All right. So as always, let's remember where we are. So we've been thinking for the last few weeks about making predictions so that our predictions are useful and maybe even the right thing for downstream agents to use. And recently, we've been thinking about this framework in which what we try to do as sort of our computational primitive is make predictions that are statistically unbiased, meaning the average of our predictions equals the average of the outcomes, not just overall, but subject to some collection of conditioning events. Okay, and we saw at least one instantiation of that framework, calibration, that had a bunch of nice guarantees. So calibration was the requirement that our predictions should be unbiased, subject to our predictions themselves. Okay, so in like d dimensions, if there's, up to discretization, something like on the order of 2 to the d different d-dimensional vectors we can predict, then the thing we wanted for calibration was that conditional on predicting some vector, the expected outcome here, since we're in an adversarial setting, expected means averaging over those time steps for which we made that prediction, should be the thing we predict. Okay, so in one dimension, this thing is sort of pretty intuitive. It's sort of asking for internal consistency checks, that our predictions should sort of look like probabilities. So for example, if we're predicting a weather outcome, then conditional on predicting a 20% chance of rain, it should rain 20% of the time. Conditional on predicting a 30% chance of rain, it should rain 30% of the time. Okay, like correct predictions that predicted the actual underlying probability of rain would be calibrated. Calibrated predictions need not be correct, of course. We gave an algorithm for producing calibrated predictions in an adversarial setting where like correct isn't even really well defined because there's no distributional process. But unlike correctness, it's something that we can audit from data and in fact enforce. Okay, so we gave an algorithm in the special, it's a very simple algorithm last class, in the very special case of one-dimensional calibration, and a general minimax kind of algorithm in the general case of d-dimensional calibration that got non-trivial calibration error in arbitrary dimensions. And the reason that was interesting, or one reason it was interesting, is we showed that from the perspective of a downstream actor, like an agent who needs to take actions and the thing we're predicting is payoff relevant to them, from their perspective, they should trust calibrated predictions in the sense that they should behave as if they are correct. Okay, amongst all of the policies they could choose, mapping the predictions we make to the outcomes or to the actions they take. Like for all of these downstream agents simultaneously, no matter what their utility functions are, they should behave as if the predictions are trustworthy and that they should just best respond to them. They should do what they would have done had our predictions been correct. Okay, that was a very strong guarantee. It was stronger than no swap regrets. Okay, and you can sort of think about this as like people love to use the buzzword like trustworthy machine learning, but like, what is the semantics of the promise you're supposed to trust? Well, I would say calibration is a good answer to that question. You should trust the predictions in the sense that you should behave in the same way that you would have had the predictions been correct. And what calibration promises you is, among other things, this is the best way you could behave. Any other mapping you might have between the predictions and actions that deviates from just trusting them is worse. Okay, that was what was attractive about calibration. Now, the difficulty, of course, was that our rates, the rate at which our calibration error, or the rate at which your regret, say, to some other policy went to 0 was really bad in the dimension. Like it was maybe reasonable in one dimension. We got t to the 3/4, and I claimed you could get t to the 2/3 by thinking a little harder. But like, in d dimensions, it sort of scaled like t to the d over d plus 1. So it, was technically sublinear in any dimension, but like, really, this is not like a reasonable thing to try to do, except in very small dimensions. Okay, so that was, on the one hand, calibration was great. It had this really strong semantics that I sort of like to interpret as trustworthiness. You should trust the predictions are correct in the sense that you should act as if they are correct. But like it's really only reasonable in small dimensions. Okay. Okay, so towards getting guarantees like this in higher dimensional problems, what I want to do today is revisit this general problem of in d-dimensional space and d-dimensional prediction problems, trying to make predictions that are unbiased, subject to various conditioning events. Okay, like calibration is a special case of this. But like maybe there's sort of two reasons why you might conjecture that calibration is hard, or maybe you conjecture that calibration is easy and we just haven't come up with the right algorithms. But like, if I tell you that calibration seems to be hard, maybe there's two reasons why you might conjecture that that is. The first is that maybe just this sort of high dimensional problem of making predictions that are unbiased, subject to any non-trivial collection of conditioning events, maybe that's hard, right? Like we don't have any evidence to the contrary so far. Our generic algorithm for solving this problem, which gets good rates, involves solving a d-dimensional minimax optimization problem. But like that's like solving a zero-sum game or like a linear program in which there are exponentially many strategies for both the learner and the adversary, because to discretization, there's like 2 to the d actions in this game in d dimensions. Okay, so maybe it's not just calibration that's hard. Maybe high dimensional unbiased prediction is hard in general. Okay, like we've given an algorithm for it, but we haven't given an efficient implementation, because like implicitly in our algorithm, it has to solve like a 2 to the d dimensional like minimax optimization problem. Or maybe that problem is not hard if you have only a modest number, like a polynomial number of conditioning events that you care about. And the reason that calibration is hard is not that it's a high dimensional problem. It's not that this game you need to solve has an exponentially large strategy space, but because you're asking for low bias on exponentially many conditioning events. Okay, so that would be better. That would mean that we have some hope of solving this unbiased prediction problem, even though it's high dimensional, for like polynomial number of conditioning events. And the only reason it doesn't give us a satisfactory solution to high dimensional calibration is not the high dimensional part per se, but because it asks for low bias subject to lots and lots, exponentially many conditioning events. Okay, so we're gonna see today that it is, in fact, that second thing that is true. Like there is an efficient algorithm, despite the very large strategy space of the game you need to solve, that makes unbiased predictions subject to an arbitrary polynomial number of conditioning events. It doesn't solve the calibration problem because that has exponentially many conditioning events, but what this is going to mean is that if we can phrase what our goals are, like incentivizing a polynomial number of downstream decision makers to have low swap regret in terms of a polynomial number of conditioning events, then we can use this algorithm, this efficient algorithm after this class, as a mechanism to achieve those goals. Okay, we just, like what having this algorithm in our toolbox is going to give us is the ability to solve problems whose solution can be reduced to low bias subject to a polynomial number of conditioning events. Okay, so that's today's plan. Questions? Okay, so let's just start by remembering like the problem we want to solve, because it's been a little while. So the thing we want to solve is given a collection of events fancy E. And remember, an event is some function mapping history and context and today's prediction to like some number between 0 and 1, or if it's easier to think about it, just 0 or 1, specifying is the event happening or not. Okay, so given a collection of events E, what we want to do is we want to upper bound, we want to control the maximum over all of the events in this set of the bias of the predictions on our transcript conditional on this event. And what is that? Well, that is just the maximum over all of these events of the sum over all of the days for which the event was active. And this is an expectation because the event can depend on our prediction, which can be randomized. Okay, so on all of the days for which the event was active, we've got the indicator function for the event of, on those days, the difference between our prediction and the realized outcome. And this is a vector. We want to control the L infinity norm of this. We want to control the maximum bias across all of the events and across all of the coordinates of our prediction. Okay. This was sort of the goal we set out for ourselves. And, I spoke this out loud as if this was an indicator function selecting out those days for which the event was active or not, but actually it can be just a weighting function specifying how much to weight each day in this sum, like the degree to which the event is active each day. Okay, so that's the goal. And let me now remind you of the generic algorithm we have for solving this problem, because we want to stare at this algorithm and instantiate it. Unlike in times past when we've done this, where we've had a generic algorithm that solves a minimax problem, and I derive like a combinatorial algorithm, and there's usually the question of, why are you doing this? Like, why don't you just solve the min-max problem? You could do that efficiently anyway. This time, the min-max problem is really big. So it's not clear at all how to solve it, and we'll have to establish that it's solvable in polynomial time in the first place. Okay, so what was the generic algorithm? Yeah. Good, yeah. So what are the things I'm going to want to be polynomial in? I'm going to want to be polynomial in the dimension, in the number of events. So when I say polynomial time algorithm, it's not going to solve calibration for us in d dimensions, because that's going to be 2 to the d event. So I want to be polynomial in the the number of events, and I guess the time it takes to evaluate each of the events. Like, if you can't even evaluate this function quickly, then there's sort of no hope. We're predicting vectors that are d-dimensional. So I'm willing to let you run in time that scales polynomially with d. Yeah. That's a good question. I think there should be. I wouldn't be surprised if there were, but I don't know of it off the top of my head. And if it doesn't exist, it really should. So that would be a good thing to prove. Yeah, so computational lower bounds for calibration. So I guess, like, it's a good question. So you could ask this question independently of rate. You could, right? So like, there are these sort of information theoretic lower bounds for the rate at which you can obtain online one-dimensional calibration. But I guess you could ask the question, okay, suppose I'm willing in d dimensions to obtain any sublinear rate. Is there an algorithm that is guaranteed to do that with per iteration time polynomial in d? I don't know the answer to that question. It would have to take advantage of the adversary, because if there was a distribution, you can of course just predict the mean. That's easy to do. That'll be calibrated. That doesn't work in high dimensions. I would guess this problem is hard in high dimensions. I bet there's not a lower bound. I bet the people who've thought the hardest about this were not so worried about computation. But I also bet the problem's hard, and so that's a good thing to go prove. Good. Okay, but what's the generic algorithm? So for each of these capital T iterations, we define essentially the appropriate exponential weights distribution. Remember how these algorithms work. They weight constraints with the exponential weights distribution and use that to define a minimax problem. In this particular case, the distribution is defined as follows. We've got weights, and first of all, like, how many of them are there? Well, we've got a distribution over 2 times the number of events times d many weights. Intuitively, one constraint for each dimension, for each event, and for each sign the bias can take, positive bias or negative bias. And the weight corresponding to the triple sign event dimension is proportional to e to the 8/2 times the sum over all previous time steps of the corresponding sign of the expected per round bias given event E. So the product of the indicator vector for event E at round T prime times the sort of instantaneous bias, the difference between coordinate I of our prediction and coordinate I of the actual outcome. Okay. And now we're going to construct a zero-sum game. So we'll define zero-sum game. Where the minimization player has strategy space that is equal to all distributions over some epsilon net, some arbitrarily fine epsilon net over this d-dimensional prediction space. The maximization player's strategy space is just the prediction space itself. And the utility function, this is the thing we're going to need to deal with today. Given a distribution over predictions for the learner and a outcome chosen by the adversary, is just the sum over all of the relevant constraints of the weight that's multiplicative weights is assigning to that constraint times the one round violation of that constraint. So sigma times the expectation of today's prediction of the indicator for the event times the one round bias of our prediction in coordinate I. Okay, and the generic algorithm plays a minimax solution PT. Okay, so this is the generic algorithm. Okay, we've seen variants of this a bunch of times. We're just computing like these weights using exponential weights over the constraints. We define a zero-sum game, which is just like, a weighted sum over all of the constraints that we care about, weighted by these exponential weights. The strategy space for the learner is a set of distributions over some epsilon net, just to make the minimax theorem apply, and we just solve the game at every rank. Okay, and the difficulty here, the reason why we can't just do this, is because, right, in general, if I have a zero-sum game with, m actions for the learner and n actions for the adversary, I could write down, like an m by n linear program and solve it to find a minimax solution, or I could run a no-regret algorithm for both players and find a minimax solution. But both of those things would have running time that scales with like m and n. And here, the learner has an exponentially large strategy space. They've got a strategy space of scaling with 1 over epsilon to the d. And the adversary has a continuously large strategy space. Okay, and so neither of those things are going to work to give us like efficient algorithms out of the box. We need to think harder. Okay, does that make sense? Okay. Okay, now fortunately, at this point in the course, we've also seen various generic ways that we can try to compute minimax equilibria of games using the toolkit we've built up from no regret learning. Okay, so let's just like remember a couple of those. One is that we could have two no regret learners play against each other. We could simulate play of this game using no regret learners for the learner and the adversary, and have them play the game for some number of rounds and return, have them basically play the game for a number of rounds sufficient such that both players have regret epsilon, and at that point return the empirical play of like the learner, and that would be an epsilon approximate minimax equilibrium. Okay, so if we could figure out how to do that efficiently, we'd be in good shape. Okay, like it's not obvious how to do that because there's again, there's exponentially many strategies for the players, so like instantiating multiplicative weights wouldn't work. But maybe you could do something else, like maybe there's some way to figure out how to use follow the perturbed leader, which allowed us to get no regret algorithms even in sort of large action space. Now, if you sort of think about that, maybe it starts by looking a little bit promising. Like, what does follow the perturbed leader do? Well, it solves like online linear optimization problems. Okay, so it was like an algorithm that ran in time, polynomial in the dimension, where the action space was continuous. So all of that is sounding promising. And where the payoff for cost function is linear in the action played by the learner. And okay, like maybe we've got like a utility function here that actually is linear in the adversary's action. So that's pretty good. Like maybe the adversary could play follow the perturbed leader even though they have this continuously large action space. But when you start thinking about how you'd implement a no regret algorithm for the learner, you sort of maybe run into some difficulties because the utility function is not linear in the learner's objective, because we've got this arbitrary event here, which is a function of the learner's action. And, or, at least if this expectation wasn't here, this would not be a linear function of the learner's action. Okay, because this event E is like some arbitrary function. Now, okay, now of course we allowed the learner to randomize. We put this expectation here exactly so that this would be linear, so that the minimax theorem would apply. But it's linear over some really huge dimensional space, right? Because these are distributions over the epsilon net. The dimension, how many points are in the epsilon net, like 1 over epsilon to the d. So although this expectation technically makes this thing linear, it makes it linear in a space that is exponentially large, has dimension 1 over epsilon to the d, because that's what this distribution is over. Okay, so it seems like we can implement a no regret algorithm for the adversary here. with follow the perturbed leader, but not for the learner. Okay, but there was another way that we had of computing minimax solutions in zero-sum games. You could have one of the players play a no-regret algorithm. So maybe the adversary can play follow the perturbed leader. And then what did we need of the other player, in this case, the learner? Well, one thing that we could have them do is we could have them best respond, right? If we could have the adversary, we could have the learner every day, given the adversary's strategy, just best respond by playing the prediction that, in this case, minimizes this utility function. Now, it's not clear how to do this either, right? Because, again, basically for the same reason, like how are they going to best respond? Well, you know, if they're not randomizing, then this is a very complicated function potentially, right? Like we don't know anything about the structure of E. And if they are randomizing, well, in expectation over the randomness, it's a linear function, but it's a linear function in 1 over epsilon to the d many dimensions. Okay, so also not clear how to have them best respond. But we actually didn't need them to best respond. What we needed them to be able to do was to implement what we called a value oracle. Okay, so what does that mean? Well, so a value oracle, the way we defined it, was some algorithm that would take as input a strategy for one's opponent, like a distribution played by the adversary, and would return an action that was guaranteed to obtain at most the value of the game for the minimization player. So in this case, the value of the game is 0, so it should take as input a distribution played by the adversary, and should return some strategy that guarantees payoff 0. Okay, how is this different than a best response oracle? Well, a best response oracle, of course, by the minimax theorem, if the value of the game is 0, would always be a value oracle. It would always return something that had value at most 0 when played against the opponent's strategy, but would, on top of that, be required basically to exploit suboptimal play of one's opponent. If your opponent is not playing a maxi-min strategy, then a best response oracle had better get you payoff that is better than the value of the game. Whereas a value oracle, which is all we really needed here, was something that would guarantee you the value of the game, even if your opponent was not playing optimally. So a value oracle has to obtain the value of the game, but it is not obligated to exploit what your opponent is doing. And so maybe there's like a sliver of hope here, even if we don't know how to implement a best response oracle. Maybe the reason for that is just because like the thing that seems hard is exploiting suboptimal play of one's opponent. Maybe the weaker goal of just obtaining the value of the game is easier. Yeah. Yes. That's right. And yeah, maybe just to like take a step back, right? Like, what is hard about implementing this algorithm? Well, we can compute these weights because we're happy to run in, time, equal to the number of weights that, it's polynomial, it's linear in the number of events and the dimension. So we can compute each of these weights. So we can define this game. Everything up through here is efficient. The only part of this algorithm that's difficult to implement is solving the game, computing a minimax equilibrium. And so the thing that we need to figure out how to do, and what I'm discussing is, for like basically finding an algorithm for solving this game. That's the proposal. That's right. Good question. Right. So like, so one thing that you might worry about is like in the algorithm here, it's like play a minimax solution, but this whole kind of approach that I'm talking about of computing a solution by simulating play of a game with no regret algorithms is only going to give you an epsilon approximate minimax solution, probably in time that runs, polynomial in 1 over epsilon. So is that okay? so if you sort of remember back to like how we analyzed this, we sort of say, okay, well, the loss, basically like you obtain, in this case, exactly the value of the game here. And so the thing we cared about in the analysis, which was the adversary moves first regret, was the difference between your payoff and the value of the game. And that was, like 0 in our analysis if you did this exactly. And so here it's not going to be 0, it's going to be some epsilon. And so the cost for that is that there will be additional loss at the end of t iterations that scales like epsilon times t. But so long as the kinds of rates we're shooting for, by the way, are like root t. So in order to get the same kinds of asymptotics that we would get without this approximation, we're going to want to take epsilon to be something like 1 over root t. And so long as the algorithms we come up with have running time that also scales polynomially in 1 over epsilon, we'll be able to do that and still maintain overall runtime that is polynomial in all of these parameters and capital T. But that's a good point that we're going to have to, or we should have thought about that. That's right. So in general, this whole approach works if rather than playing, an exact minimax solution to this game, you play an epsilon approximate minimax solution where epsilon is smaller than 1 over root t, something like that. And you get the same theorem at the end. Now, of course, something is going to be specific to this game, and that's our ability to do it. Like, not every game will you be able to efficiently do that, but for this game, you will be able to. Good questions. Other questions? Okay. So we've remembered one generic algorithm. Let's remember one more generic algorithm, which is how to compute an equilibrium, approximate minimax equilibrium with a value oracle. Let's see, my board planning is not very good, but suspecting that I'm going to want to keep these algorithms around while I write other stuff, let me try to write this algorithm here. Okay, so here was our generic algorithm for computing a minimax equilibrium. In particular, using a no-regret algorithm and a value oracle. So what are we given? A value oracle. What kind of object is a value oracle? Well, in this case, we're going to be using it for the maximization player. No, we're going to be using it for the minimization player. And so it's going to be a mapping from distributions of the maximization player's actions to actions for the minimization player, right? So it says, given a potentially mixed strategy of one's opponent, of the maximization player, what is a deterministic action that I can play so that I'm guaranteed to get payoff at most the value of the game? Okay, so we're gonna, in the generic algorithm, we're assuming we've been given this. Of course, we're gonna need to implement it. And also an online, let's say in this case, linear optimization algorithm for the maximization player. Okay. Let's say with regret guarantee R of t, meaning, this online linear optimization algorithm, say follow the perturbed leader, promises that no matter what happens, the regret that it gets to the best fixed action in hindsight is bounded as some function of t, like R of t, probably going to be something like square root of t if we're using the algorithms we've been studying. Okay. So what we're going to do is we're going to do the following. For sufficiently many rounds, such that the regret of the maximization player is less than epsilon. So such that if we look at the average regret guarantee for the maximization player, it's at most epsilon. And for each of those rounds, we get an action B of t for the adversary from the no regret algorithm. We choose an action for the learner by plugging the adversary's action into the value oracle. And then we need to give some feedback to the no regret learning algorithm. And so we feed loss L of t, which is equal to the utility function of the game, to the online linear optimization algorithm. Okay. And at the end, when this is all done, after capital T rounds, we return a bar, which is the distribution, the uniform distribution over the actions played by the learner over this interaction, the output we got from the value oracle over these T rounds. Okay, so this is an algorithm we analyzed months ago at the beginning of the class. And what we proved is that assuming that, the no regret algorithm really does have regret guarantee R of t, and assuming that this really is a value oracle, that every day when you play action AT against action BT, you obtain the value of the game, then the distribution this thing outputs is guaranteed to be an epsilon approximate minimax solution for the minimization play. Okay? Trip down memory lane. Yeah. That's right. Yeah. So just riffing or explaining that to maybe people who don't know all of the references. Yeah, like there is sort of like a nice structural theorem that is revealed by the fact that there is this dynamic that sort of converges to an epsilon approximate equilibrium quickly over, after only, if we use a algorithm that has regret guarantee root t, this will converge after 1 over epsilon squared many rounds, and outputs a minimax strategy that happens to be a uniform distribution over a set of items that has support equal to the number of rounds. In this case, 1 over epsilon squared. Right? It means even if your game, there's no dependency here on the number of actions, or maybe, maybe the regret guarantee will depend logarithmically on the number of actions of the adversary, but it's independent of the number of actions of the learner. And it's telling you that there always exists an epsilon approximate minimax strategy for the learner that is sort of sparse, that has support over only 1 over epsilon squared many pure strategies. So if epsilon's a constant, it has only constant size support, no matter how big the game is. It's not obvious a priori that that had to be true, right? Mixed strategies in principle could have full support. It's saying if you want an approximate mixed strategy, there's one that is sort of sparse. So that's kind of cool. You could prove theorems like that also by just starting from exact min-max, exact equilibrium strategies and sampling from them and applying things like turn-off bounds. But if you did that, you might pick up, you have to think about whether you'd pick up logarithmic dependencies on the action space of both players. Here you do not depend at all on the strategy space of the learner, which is interesting. Oh, yes, indeed, cool structural fact. Yeah, I mean, the stuff also comes up if you're interested in like the query complexity of Nash equilibria and stuff. Like, like if you have a really big game, like how many queries do you need to make to the utility function to figure out minimax equilibrium? And this is a very query efficient algorithm to do it. So, sometimes people think about these kinds of things. Cool. Okay, so what do we need to do to make this? Okay, so first of all, roadmap. This is an algorithm to compute an equilibrium of a general game, of a general zero-sum game. We need to compute an equilibrium of this zero-sum game. So we would like to instantiate this generic approach with this game. Now, what does it mean to instantiate this generic approach? Well, we need to demonstrate that you can efficiently play a no-regret learning algorithm. In this case, it's going to be follow the perturbed leader for the adversary. And you can efficiently implement a value oracle for the learner. Okay, so that's where we're going to need to use the structure of the game to show that we can like efficiently run follow the perturbed leader for the adversary and efficiently implement a value oracle for the learner. If we can do that for this game, that means we can compute an approximate equilibrium of this game, which means we can implement this generic algorithm efficiently, thereby solving this low bias prediction problem. Okay, roadmap makes sense. Okay. So let's start with follow the perturbed leader. Let's sort of show that we can, or that it makes sense to run follow the perturbed leader in this setting. Okay, so I mean, follow the perturbed leader is, an algorithm that gets no regret in any online convex optimization problem, in time that, depends polynomially on the dimension and like other scale properties. Okay, so the only thing we need to like verify is that we can represent the problem of getting low regret with respect to this utility function as a, d-dimensional online linear cost minimization problem. Okay, so we're almost there. We just need to like verify a couple of things. Okay, so basically, like, remember, what is the problem that follow the perturbed leader solves? Well, every day it plays a vector in C, or every day it plays a vector in its strategy space, which I now realize I've confusingly called C. And then it receives a cost vector from the adversary, which we used to call C as well, but try to call these things different things. You follow the perturbed leader plays a vector, the adversary plays a vector. The cost experienced by follow the perturbed leader is the inner product of these things, and it gets no regret in this setting. So we need to show that the problem of getting no regret to this utility function can be represented as a problem that follow the perturbed leader solves. Okay. So it can. So let's define the following cost function, which is in the form that we want. Okay, so let's define cost function. I'll call it CT of PS. And it's just going to be the sum over all of the signs and all of the events and all of the coordinates of the weight that the generic algorithm assigns to the corresponding constraint of the expectation of the prediction drawn from distribution P of the indicator function of the event times SI, the ith coordinate of the action chosen by the adversary, which I'm going to observe, since this is, among other things, the sum over some stuff and then the sum over I of something times SI, can be written as the inner product of S, the vector chosen by the adversary, and some cost vector CT that I'm going to write down in a moment. And the salient thing about CT is that it depends on the strategy of the learner, but not on the strategy of the adversary. Okay, so CT is a d-dimensional vector that depends on the strategy of the learner. What does it equal? Well, in coordinate I, it equals the sum over sigma and E of the weight assigned here in the algorithm to constraint sigma E and I of the expectation of the indicator for the event. That's it. Okay, and sort of just noting this is exactly equal to this, except we're not summing over I, and we're not multiplying by SI. And that's because summing over I and multiplying by SI is represented by the inner product here. Okay, so I'm going to define this cost function, which is the sort of thing we could use to get no regret with respect to using follow the perturbed leader, because every day the learner chooses, or in this case, person running follow the perturbed leader, who we're also calling the adversary, which is a little confusing, but the person running follow the perturbed leader chooses a vector S. Their adversary, who is our learner, chooses a vector P, but which we translate into some vector C. And then the cost is just an inner product. This is the kind of, getting no regret with respect to this cost function C is something that follow the perturbed leader can do. It's an online linear minimization problem. So what's the claim? So the claim is, if on some transcript, when we look at the regret that someone running follow the perturbed leader against these cost functions has, so what's that? That's the sum over all time of, well, what's their experienced cost? It's the sum over all time of the cost they experienced at that round, so the inner product of the action they chose at that round and the cost vector from that round. And if they have a regret bound, what that means is that this accumulated cost over time is not larger than the cost they could have obtained by playing their best fixed action in hindsight, the action that would have minimized their accumulated cost had they consistently played it. So the action that would have minimized their accumulated cost over all time had they consistently played it against the realized sequence of cost vectors. Okay, if they have a regret bound of alpha, meaning they are doing at most alpha worse compared to the best thing in hindsight, with respect to these cost functions, then the claim is that they also have a regret bound of alpha with respect to this utility function that we actually care about in this game. Okay, so in particular, when we now look at the sum utility in this game, which is a function of the actions played by the adversary and the learner, and is now something that the adversary wants to make big. It's a utility function, not a cost function. That this is at least the largest value they could have obtained in hindsight over all such strategies of the utility in this game, fixing what the learner did, optimizing now over actions of the adversary minus alpha. Okay, so the claim is that, although this is not exactly a utility function that sort of fits into the follow the perturbed leader framework, we can define this like different utility function, which transparently does fit into the follow the perturbed leader framework. It's just an inner product. We're minimizing cost. Okay. Importantly, the thing we're taking an inner product of can be computed independently of S, such that if we run follow the perturbed leader to get no regret with respect to these losses, we will have, in fact, automatically gotten no regret with respect to these utilities. Okay, so if we want to implement an algorithm for the adversary here that gets no regret with respect to these utilities, which we do, it suffices to run follow the perturbed leader with respect to these costs. Okay, so that's the claim. Right? If this is true, then we will have shown that you can implement a no regret learning algorithm efficiently for the adversary here. It's just follow the perturbed leader on this transformed game. Does that make sense? Okay. All right, so how come? Well, we need to sort of write this utility function in terms of this cost function. That's the first thing we need to do. Okay. So what I want to do is I want to, looking at this utility function, I want to expand this out. Right, like in particular, we have this difference here. And so I want to expand out this into the difference of two terms. Right, we've got some weighted expectation of the predictions minus some weighted expectation of the actual outcomes. I just want to express the utility function explicitly as the difference between those two terms. Okay, so we've got our utility function. Observation one is I can divide it out as the sum over all of the constraints of the weight that our algorithm assigns to each constraint. Of the expectation of the event indicator times just S hat of I. Okay, so I've taken all of this and I've multiplied it by the prediction of the learner. And that what I've left off, which I now have to subtract off, is just what I've written here as CT of P and S. Okay, so the part that I extracted out from here is exactly the sum over all of the constraints of the weight of the constraint of the indicator of the event times SI, the ith coordinate of the actual outcome. Right, the first term is all of this times SI hat. The second term, which we're subtracting off, is all of this times SI, which is exactly this thing that we called CT. Okay. And I want to observe that this, just as, this thing, which I will write as U hat T of P, like a salient property of this term is that it does not depend on the actual outcome S at all. It does not depend on the action of the adversary. Only depends on the weights, which depend on the past, not the action of the adversary. The events, which can depend on the past and the current context, but again, not the current realization of the adversary. And it depends on the learner's distribution, but it is entirely independent of today's choice by the adversary. Okay, so the relevant thing here is that I can write out this utility function as a difference between two terms. The first term might be complicated, but it does not depend on the action of the adversary at all. And the second term, which does depend on the actions of both players, we just showed is not especially complicated. It's just a linear term in the action of the adversary. And so that's the kind of thing we can follow the perturbed leader on. Okay, so complicated term, but independent of the action of the adversary, minus term that depends on the actions of both players, but is not complicated. It's linear in the adversary's action. Okay. So, we're interested in regret here, regret to the best fixed action in hindsight. So we're interested in looking at the maximum over anything the adversary could have done in hindsight, summed over all of the rounds of the utility function, fixing what the learner did, but maximizing over fixed actions S of the adversary. Now we know from this decomposition that we can write this as the maximum over all of the adversary's actions of the sum over all of the rounds of, this utility function we now know can be decomposed as the difference between two components, U hat of T and CT. Now, U hat of T is complicated, but it doesn't depend on the action of the adversary. And the thing we're maximizing over here is an action of the adversary. So whatever choice we make at this outer maximization does not affect this first term. Okay, and so as far as this maximization is concerned, this thing's a constant. Okay, and so we might as well maximize just over the inner term. Okay, so we might as well minimize over the, we're maximizing over negative of the inner term. That's like minimizing over the inner term. So this is equal to the sum over all of the rounds of UTP, or UT of PT, the learner's action. That's just a constant as far as this optimization is concerned, minus the minimum over all of the adversary's actions of the sum of the cost component of this function, CT of PT and S. Okay. Right, so we're maximizing over a difference between two terms. The first term didn't depend on the variable we were maximizing over, so it didn't affect the maximization. Maximizing over the negative of the second term is the same thing as minimizing the second. Okay. Okay, but now looking at the minimum of this cost function over all rounds, that's the kind of thing that if we were running follow the perturbed leader over this cost function, we would have a regret bound on. At the minimum of the second term over all rounds is at least the actual realized value of the second term minus alpha. That's the presumption that we have this regret bound here. So this is at most the sum over all of the rounds of u hat t of pt minus the sum over all of the rounds of u hat t, right, of ct of pt and st plus alpha. That's just applying the hypothesized regret bounds that we have on C. Okay. But now there's no minimization, there's no hypotheticals. This is just the realized utility over all of the rounds, right? So this is nothing more than the sum over all of the rounds of, the actual realized utility in the game. Plus alpha. Okay, and that's the regret bound we wanted. What do we have? We have that the sum of the realized utility of the game is at least the maximum utility that could have been obtained in hindsight minus alpha, which was what we want. Okay. So, yeah. Yeah, so like basically, right, you can sort of internalize a little lemma that would have had you be done at this point. So basically, we've proven all of these theorems about minimax equilibria in zero-sum games, okay? Now, all of that, it doesn't really need to be a zero-sum game. All of that works if I shift your utility function by a term that can depend in arbitrary ways on what your opponent does, but not on what you do. That might break zero-sumness, strictly speaking, because the sum of the utilities depends on what your opponent does. But it means that you can ignore the part of the utility function that makes it non-zero sum from the point of view of thinking about regret and everything we proved about sort of minimax equilibrium. So that's sort of what's happening here. We're sort of saying, look, follow the perturbed leader can optimize this part of the utility function. That's not the whole thing, but the part that remains, it's not just a constant. If it was a constant, it would be obvious it didn't matter. It's not just a constant. It can change from round to round. It depends on what your opponent does, but if it does not depend on what you do, then it is irrelevant from the point of view of regret. Because this term will be the same both in the world in which you actually played some sequence of actions and in the counterfactual world we are comparing against where you play some fixed action. Exactly, because the benchmark is fixing the opponent's actions. When we look at the difference between your payoff in the real world and the benchmark, this term cancels out, and only this matters. So whenever you can do this, if you can obtain regret with respect to the linear part, then that's enough to obtain regret in the full game, even though, strictly speaking, this is not an online linear optimization problem. Like, in all relevant aspects it is, because the thing that makes it not like an online linear optimization problem is independent of your own actions. That's what's happening. You could like break that off as a little mental lemma and be done once you make this observation. Yeah, good. So, right. So why does this not matter? Well, it's because when we talk about regret, the benchmark fixes your opponent's actions and we get the cancellation of this thing. Now, it actually also extends to equilibria in the sense that, suppose you have some utility function like this, and your opponent has some utility function that is like CTPS minus some term that depends on only your action. Okay, so this is not a zero-sum game anymore. Okay, but suppose you pretend that the only part of the utility function for both of you is CTPS, and you solve that zero-sum game. You get a min-max equilibrium in that zero-sum game. The claim is that will also be an equilibrium in the original game, because from both players' perspectives, like put yourself in the perspective of like the maximization player, you thought you were, minimizing this. If I actually tell you, oh, no, your utility function is this whole bigger thing, this other part I just surprised you with is strategically irrelevant to you. It changes your absolute, level of happiness, because now, this is here, but you can't affect it. And so equilibria is just about best response. You have to be doing as best as you can given what your opponent is doing. And if I add some annoying term that makes you really sad, but that you can't affect, then you might be really sad now, but since you can't affect it, if you were playing a best response before, you're still playing a best response. Yeah, I don't know. I mean, I think that, yeah, like it's maybe interesting to think about. So the mathematical claim I'm making is that there's some larger set of games that are not zero-sum games, but are strategically equivalent to zero-sum games. What is this larger set? Well, you can obtain a game in this larger set by starting from a zero-sum game, and then arbitrarily modifying both players, either player's utility function, separately modifying the minimization player's utility function, and separately modifying the maximization player's utility function. So long as the modification adds or removes terms that depend only on the action of the other player. Okay, then I claim that these same algorithms that compute the equilibria of zero-sum games also compute the equilibria of this larger set because of this strategic equivalence. Now, I guess, yeah, like, what is the nature of this set of games, which is strategically equivalent to zero-sum games? Are they, in what sense is it bigger? In what sense is it more interesting? Not everything carries over, right? The games don't necessarily have a value anymore, because even though you can still compute equilibria by running these no-regret algorithms against one another, you could have two things that are both equilibria of the game defined only by C, okay? And so take the same value on C, but such that this additional term evaluates to something different than these two equilibria, right? So these games do not have a value anymore, even though you can still compute the equilibria of them by running no-regret algorithms. So this is another, yeah, it's a good question. Like this is, I don't know of this fact being really like recorded anywhere. Like, yeah, what is this class of games that is like strategically equivalent to zero-sum games? Every once in a while, it is useful to like take advantage of it, but I don't know of it being systematically studied. Maybe because it's just not interesting or whatever. But yeah, maybe like another thing to, good to know, exactly. And it is occasionally useful. So I don't know if there's like some, yeah, more systematic way in which it is useful. Okay, good. Okay. Okay, so the upshot is that we can implement follow the perturbed leader efficiently. How? We just run it on an online linear optimization problem, which we know it runs efficiently for, defined like this. Okay, and we get regret scaling with root t, which means that this whole algorithm instantiated with follow the perturbed leader is going to run for like 1/epsilon² many iterations. Okay, so the algorithm, every step of follow the perturbed leader will run in time, like linear in D. The number of iterations of this algorithm is like 1/epsilon². I guess computing the losses to feed to follow the perturbed leader involves computing these weights, and so that takes time that is linear in T and D and E. So far so good. We're polynomial in all of the things we care about. And the only remaining thing to do is to show that even though we don't know how to implement like a best response oracle, we can implement a value oracle, which is the only thing we need here. Okay. Makes sense. Yeah, so maybe just to like, well, okay. So here's the claim. For the game with utility function ut, this one, given any distribution qt, it's a distribution played by the adversary. Remember, the adversary is running follow the perturbed leader. So they're going to be playing distributions over vectors in this space C. We can implement the value. We can implement a value oracle as follows. Okay, when you plug in the adversary's distribution qt into the value oracle, what do we need to get back? We need to get back an action that the learner can play, so an element of C, that guarantees that in this game we get value, we get payoff 0. Okay, even if it's possible to get payoff below that. It's not a best response. It doesn't have to be a best response oracle. Just has to get payoff 0 because the value of this game is 0. Okay, so what's the value oracle going to do? It's just going to return the expectation over a state sampled from the adversary's distribution of the state. Okay, so it's sort of going to copy the adversary's strategy, right? The adversary plays some distribution. The learner just plays the expectation of that distribution. Okay, easy peasy, not especially smart, not like a best response oracle, like definitely not trying to do any kind of reasoning and exploit errors of the adversary, avoiding entirely thinking about all of the parts of this utility function that make it difficult to compute a best response, like the structure of these events and the contents of these weights, like the value oracle doesn't even know about the events, right? It's just reading off the expectation of the distribution it was handed. Okay, makes sense. That's the claim, at least. Okay. But like, I guess once I say it, you can probably sort of see why it's true, right? Like, you know, how come we can't implement a best response oracle? It's because of these complicated functions E. We don't know how to optimize. We don't know anything about these functions. But, you know, these functions E, these weights, all of the complicated stuff, it's just serving to be like a multiplier in front of a pretty simple term. The difference between our prediction and the adversary's action. And remember, we already sort of took advantage of the fact over here that all of this complicated stuff, it's independent of the adversary's action. So if we're interested in the expectation of this quantity over the adversary's action, that expectation sort of can be taken all the way through this complicated stuff, because the complicated stuff, as far as the adversary's action is concerned, is just a constant, and put here. And so all that matters for the expected payoff here is actually the expected value of the state chosen by the adversary. And the value oracle is just matching them, okay? Causing this difference to be 0, which happens to be the value of the game and is all we needed to accomplish to implement the value oracle. Okay, so best response oracle, don't know how to do it, don't know how to optimize this function because it's complicated. Like in particular, these events E can be arbitrarily complicated functions. D-dimensional optimization of arbitrarily complicated functions is hard. But for a value oracle, it turns out for this utility function, we don't need to worry about. Okay, so just to dot the I's and cross the T's, you know, what is the expectation of this utility function when we say S hat is what we get out of the value oracle, just the expectation of S drawn from Q when the adversary's strategy is Q. And then we ask, what is the expected value of the utility function when the adversary plays distribution Q, so expectation of the prediction over Q, and the learner plays S hat, the thing that is spit out by the value oracle. Okay, like what we need to show is that this thing is 0. That's what a value oracle promises. Well, it's the expectation of this thing, expectation over S. And as I said, well, okay, this is actually a constant. This term is not a constant, but it doesn't depend on S. So it is a constant as far as the expectation over S is concerned. And so we can write this as the sum over sigma E and I of the weight that the algorithm assigns the corresponding constraint times sigma times E of T S hat and XT. No expectations here so far because we are not randomizing. The learner is playing a pure strategy. They're just playing S hat. Okay, so this expectation is, well, the expectation over a pure strategy, so it disappears. Minus the expectation over the adversary's strategy of the only place where the adversary's strategy actually shows up in this expression, you know, just the expectation of the strategy itself. Okay, but you know, S hat is by definition also the expectation of the adversary's strategy. And so in particular, this is equal to this in every coordinate. So this term zeroes out. And so the whole thing zeroes out. Yeah. Yeah, you might worry about that, but I think you needn't, in that we didn't care what the epsilon net is. So this thing only ever plays like 1 over epsilon squared many discrete points. As you observed before, it's playing, you know, only a small number of pure strategies. And so you can just use them as is. If you were worried about it, you could round them to you know, a million decimal points of precision and eat the loss, maybe this wouldn't obtain value 0, it would obtain value epsilon. Exactly. So remember, this discretization is just sort of like an annoyance. Nothing depends on it. And so I don't think you actually, I think it's totally rigorous even if you don't do anything to like round these points. But if you are worried about that, then epsilon, there's no dependence here on that epsilon, the discretization. So if you are worried about that, round this expectation to 100 decimal places, and now it's in your epsilon net. Yeah. Yeah. I think there's like a bigger place where you should be concerned, which is that I was like, okay, like, let's just play the expectation of this distribution as if that's something we have access to. But follow the perturbed leader does not actually give you a closed form expression for the distribution. Follow the perturbed leader gives you an efficient sampling oracle for the distribution. And so had you asked this question, I had a couple of answers in mind. No, you asked a good one. Okay, so basically there's sort of, okay, in various common special cases, you actually can still get a closed form expression for the expectation. So for example, if the convex space C that we're optimizing over is the unit rectangle, every coordinate can be between 0 and 1. Or if the convex space C we're optimizing over is the d-dimensional simplex distributions. In this case, you can sort of, right, like, what's follow the perturbed leader doing? It's adding noise, and then it's solving a linear maximization problem. And, you know, over the simplex, the linear maximization problem is always, you know, at a vertex. Over the rectangle, the linear maximization problem just independently optimizes over each coordinate. And so there, you know, if you write, you know, if you think about it and, you know, write it down, you can get closed form expressions for this expectation. In general, though, for an arbitrary convex region, you might not be able to, in which case you're going to have to approximate this. Now you can do that. You can, we have an efficient sampling oracle. So what I can do is I can sample a bunch of times and take the empirical average, and, you know, this convex region, in any case, we had to assume was bounded. And so you can apply a Chernoff bound and get something that is not exactly equal to the expectation, but epsilon away. In which case, what you will get here is not exactly 0, but epsilon. But that's good enough in that, you know, I think we may have even shown this at the time. If you have an epsilon approximate value oracle, something that gets you within epsilon of the value of the game, then you get, you know, a 2 epsilon approximate minimax equilibrium instead of an epsilon approximate minimax equilibrium. So fortunately, for various reasons, you're right that we might not be able to do this exactly. One reason is what you raised, which is that we're supposed to be playing over some epsilon net anyway, and we need to like discretize in low order bits. Actually, I think the more serious reason is that we might have to estimate this quantity from sampling, because follow the perturbed leader, all it does is gives us an efficient sampling oracle for this distribution. But fortunately, our methods are robust to approximation error. The approximation error just pulls it. Okay. So the final algorithm, you know, pulling the thread all the way through, is this, right? Like the final algorithm is indeed maintaining these exponential weights over, you know, the constraints, 1 or, you know, 2 for every event cross dimension. At every round, it is constructing this very large game. Then what is it doing? It is computing not an exact, but a 1 over root t approximate minimax equilibrium for that game. How is it doing that? It is running this interaction for 1 over epsilon squared, which is t rounds. It's running this interaction for t rounds, where for the adversary, it is playing follow the perturbed leader, not over the original utility functions, but over this derivative of them. And for the learner, it is just copying the adversary's strategy at every round. The learner is just reading off the expectation of the follow the perturbed leader distribution. And the thing we output at the end is just actually the uniform distribution of the learner's strategies, which in this, there's hardly a learner here. Like what the thing that you're outputting at the end is the uniform distribution of the expectation over the adversary's strategies, right? So it's really just the follow the perturbed leader distributions that you're outputting at the end. Okay. You play that, okay? And what we showed is you can implement all of these moving parts in polynomial time. So the upshot is, if you have some d-dimensional space, you've got some collection of events you care about that you can each evaluate in polynomial time. You know efficiently, given the history and the prediction and the context, whether the event is active or not. You can efficiently make predictions, efficiently meaning polynomial in D and T and E. You can efficiently make predictions that have bias with respect to the worst of these events, scaling with root T times log of the number of events times D. Yeah. Yeah, so we need, what do we need? We need, yeah, good. So pulling the thread even further, how do we implement follow the perturbed leader? Follow the perturbed leader is a reduction to it's a reduction to just linear optimization over C. Now, in this case, there's nothing to do there because we've already assumed C is some continuous convex space, right? Like if C was a discrete space, like all paths in a graph, then you'd need to like say, well, Dijkstra's algorithm. But generically, linear optimization over a convex space is something we can do, or okay, at least approximate in polynomial time. If you pull that thread hard enough, you get to like ellipsoid or something, and you don't want to do that. But you can, yes, polynomial in D. And of course, you need to compute like the numbers corresponding to this loss. And I think I erased them, but those numbers, that's easy to do. Those numbers are all just, like, they're just algebraic manipulations of these numbers. Okay, so because it's a continuous optimization problem in D dimensions, you can solve linear optimization in time polynomial in D. Yeah, exactly. So one of the things your polynomial in is just, the running time it takes to evaluate each of these expressions, which is, just to like evaluate the utility function. But yeah, if you pull the thread hard enough, you eventually get to ellipsoid, but like everything is polynomial in the relevant parameters. Okay, so it doesn't solve for us calibration efficiently because there the number of events we cared about was exponential in D. But it does solve for us any problem for which the number of events we care about is only polynomial in D. And we'll see next time I teach some interesting cases like that. I say next time I teach and not next class because next class, Natalie will be telling us about some very recent progress on no swap regret algorithms that I am looking forward to, especially if Natalie can successfully videotape it, because I will be in Switzerland, so I'll have to watch the recording. Okay.